So I'm recording. Okay. Yeah. So you are able to see the screen, right?
Yes, sir.
Yeah. Okay. So now in our last class, we have already started our last week we discussed the solar system inventory. Then now we have gone to our specific objectives, of this course. So as already I mentioned, this course is about geological aspects of this planetary explorations. Okay. So this already last class yesterday we have discussed we would like to find out what is the present state, then the past state, say. Then how do the present and past states compare with those other objects in the solar system. So these are the main broad objectives about this planetary geology. Okay. Then we have also discussed about astrobiology, which is of course linked to planetary geology because water and other things also comes into picture. So this is also very important the aspect of this planetary explorations. And then, as already I told you, in the olden days, so Viking and those things were, they were launched these missions, for essentially to search for life on Mars and other things also. Okay. So now what has happened was initially the subject was not that much, what you can say, the methodology, how to do, how to proceed this. It was not there in the starting point of it, and because the main objective was the military and political issues was it. Then slowly say as subject progressed, so the objectives and other things have been clearly stated, the methodology, how do we proceed and other things also. And then this was a strategy we set. So nowadays the strategy is, if you want to study about any planet or any moon or anything like that, say. So now the first thing is, you do like a systematic procedures are there. So first you go through our telescopes, okay. So with these telescopes, say. So now you decide, what are the geological process, or from those you observe closely all those things. Now once you are convinced, say, then you go by flybys basically. So like Voyager 1, Voyager 2, I told you, just you fly above that planet, and then get to know some more details, because you can take photographs, very close to that planet, so that images people analyze to see whether we can send a mission to that planet or not. Now once a flyby is done, say, the next one is we go for this these orbiters. Okay. So that means we are not going for any landers, we are not going to land on the planet. So these orbiters job is, they rotate, basically they revolve around that planet in several directions, and then they will get you the topography information, the gravity field, magnetic field, all other some geophysical data sets itself. So with that, you take a decision, say. Now the next step comes landers basically. Okay. So where you launch a rover, it lands on that particular planet and it does some experiments like a drilling, or maybe, yeah, so seismic testing or whatever testing they do, active or passive seismic testing we say, and then we get some more information also. Now here, of course, what we said was the best thing, is a human missions. If you send a humans, it has a lot of advantages, because human beings say, okay, so we are better. Once you look at an object, we can come to quick conclusions and others also. But what happens is sending humans is very risky kind of thing. So now in the planetary, these explorations, and now what people say, as I already told you in the last class also, like for one human mission is equivalent to some 100 or maybe 200 robotic missions one can do. And of course now this field of robotics basically it has advanced a lot. So now the present philosophy is you send as much rovers as you can, and you improve its rovers mobility also. So once it has landed at some place, it should be able to go to several other places also, and then collect data and then send back to Earth. Or maybe sometimes, like I told you, it's a Chinese thing say. So it had a landed rover also was there, and then it collected the sample, and then it came back to Earth itself. Okay, so these are the strategies now. Of course, human missions are also planned, but this is the now the broad methodologies. And now it has been, initially it was political and military, but now all the things have been now been written up and very well understood also. So this was I showed you in the last class also, like how many missions have been undertaken till date. Okay, like how many flybys, how many orbiters, how many impactors, landers, rovers, samples, human missions, and all those things have been. This is the current thing. And of course, in the next 10 years, these are highly evolving areas. Obviously, these things are going to increase. Now, in moons, there are about 6 human missions have been done on the moon itself. And then, as already I told you in the last class, once a mission gets over, or the mission is successful, whatever results they get. So generally they discuss in these conferences in the science and nature journal specialist comes. That is the first paper. Just they will disclose the data, and then after rigorous review, after analyzing the data, they publish in the PsychRS or JGR, these type of journals itself. So this is a current trend in planetary explorations. So now, as already, so initially there was no methodology, but now the methodology is very, very straightforward. Telescopes, then comes flybys, then comes orbiters, then comes landers, and maybe rovers, and then mobility, then maybe human missions, and then so all the things are step by step, step by step, step by step they do. And then how the results are also published. The results will be kept open for public. Anybody can take this data, and then you can write your own PhDs, or maybe you can do whatever you like, and you can also present your own interpretations also for the data set itself. Okay, so this is how the methodology. And now coming to this planetary geology, say, okay, now we will come to much more, the definitions and others also. Generally, in your civil engineering, there used to be a course on engineering geology, okay, because of, some courses or others that has been deleted. But in universities, people do this engineering geology. But in our IITs, the geology has been combined with soil mechanics course, and I think 1 or 2 units maybe you study about this geology. Now, if you see this geology, say, so geology is basically, it is linked to solid surface research. Okay, so you would have known, right? Geology means you will study, you see, the types of rocks, igneous rocks, metamorphic rocks, and then faults, folds, all those things will be there. So it is basically a solid, the surface research kind of a thing we can say. But of course, in our solar system, so if you want to do geological things, the planets are limited. So if you want to do these geological studies, the best thing is terrestrial planets only, because Jupiter and other gas giants, because they don't have any solid surfaces where you can land or you can take photographs, the mountains and other things are not there. So it limits, to study the geology of those type of planets. So mostly geology, if you want to do in solar system, you have to focus closely on terrestrial planets only. And of course, icy things also one can do, but of course, we will come to that one at a later stage. Okay. And then is a planetary geology say. So it is basically a broad and interdisciplinary research. It is not like independent research area, because we have a borrowed expertise, intellectual, many tools and other things, softwares and others, technologies from astronomy, astrophysics. We have to work closely with all those people itself. Of course, its fundamental principles are still geology, whatever you have studied in your civil engineering course itself. But here, planetary geology, what happens is, because we don't have geological studies which have been carried on other planets, so we completely work on remote sensing one. That is mostly on the images, So whatever the spacecrafts have taken, say, using that images only, you have to understand and you have to infer how that geological aspects and other things have to come into picture. So geology on Earth is different. Planetary geology is entirely different. Principles are same, but Earth geology, it is very easy. You can collect the rock, you can test the samples. It becomes very easy. But if you want to study geology of Moon and Mars or other planets, it is extremely complex. So you have to do heavily. You have to rely on this remote sensing or these rovers where they are testing and other things also. So it is very much observational kind of subject only, and in many respects it is not as much experimental. Basically, geology means a lot of experiments we do, but in planetary, we can't do that type of things. Mostly observational kind of thing itself. And of course, we do all kinds of the methodology principles are almost exactly same as whatever geology you do on Earth, but mostly observation. So now, and here also, and the geologists, if you want to do experiments on other planets or whatever, mostly you can't do laboratory experiments. If you want to simulate an impact or something like that, say, the planetary impacts are very complex kind of a thing. So you have to do computational models, in computers, you have to simulate them and then compare with the, like that, and you have to draw some analogies or some conclusions based on this numerical experiments also. So now, so the subject planetary geology say. So now, when it was born or when this subject came into picture, of course, this subject was born not recently. Like people think after going to moon only, this became more popular. But the planetary geology was a very old subject. It was, built long back itself. Like Galileo and others say, they used to do these telescopes, and then they used to observe, the impact craters or volcanic craters on moon and others, and they have drawn a lot of maps also. So this planetary geology discipline, it is not only the recent area, but the subject was interest was there in the olden days, in something around 1800 or maybe 1700 itself. The subject was born basically. Okay, and of course you can trace it back to planetary astronomical observations. People used to. I told showed you Christian Huygens. That he has drawn some maps and the craters and other thing, mountains, marking those things. So from that time it started. And of course, the Apollo missions, they made this planetary geology a very, very popular subject itself. So here, so of course, in the olden days, it was very difficult to establish, only through telescopes, you see, you can't judge them. So mostly they say that previously you would have seen James Head lecture also. So all those things were they used to tell the astronomical objects. Once you know the geology, they become a geological object itself. So now, so of course, if you see geology of Earth, geology or geomorphology, in initial stages, it was mostly descriptive kind of thing. Now in 20th century, as already I showed you, we had this process-oriented approach. We know all the step by step, the things have come in the 20th century. Now, similarly, planetary geology also has gone through a similar history itself. So in the olden days, say, like once these flybys or orbiters, this moon I am showing you here. So this is a very interesting place in called as a Tycho, the region. So you can see how this has been formed, and this is also a very famous region. Apollo 12, I think they did. I think Copernicus, that they have named this place as a Copernicus area itself. So once these images came up, say during flybys or orbiters, automatically this planetary geology picked up the momentum itself. And what people used to do is when I look at these photographs, automatically in the mind, what the people used to ask is how this, this typical shapes, like it looks like a crater, or whether it is a volcanic region. Volcanic craters also we have like this volcano, mouth of a volcano. So here, lava will come. So whether it is this crater has been formed due to a volcano, or whether it has formed due to a meteorite impact or asteroid impact. So these questions was raised in the olden days itself. So in the olden days, people used to find out from the images only. They used to come to some kind of conclusions itself. And of course, once this and impact cratering was not, there was not much support for that issue itself, because people were not, the process of familiarity with meteorite impacts was not there. So they said it was all volcanic craters or the volcanic origin itself. And then in Apollo programs, once these astronauts came and then full exploration, so they became a lot of samples also. So then this subject, has evolved from this Apollo missions. It became more popular kind of thing. So the main objective, or what we try to do in the geology, is this is the most important question. Like you say, how one can study, say, the geology of a planet or any satellite, like moon or whatever, without actually going there. So this is a fundamental question which we, this planetary geology say. So we'll try to address actually. So you are not going to there by looking at remote sensing and by looking at those data sets itself. So you should be able to tell us, the geological aspects. You should be able to mark where are the faults here, like how this geological formation has happened, whether it is a volcanic crater or whether it is a this impact crater, or it is something else, or whether it was a lake basin. And then you should be able to map all the geological features, like you see where are the faults located here and what type of rocks they are. And you also should be able to tell us what is the age of the crater, age of the rocks, and then you see whether there are any boulder faults or fault movements or landslides are there or some dust storms are there. So all those aspects have to be done. So we are not going to that place, but by looking at these remote sensing images, you should be able to collect all this information. So that is the main objective of planetary geology. So this is a fundamental question. So how one can study the geology of a planet or a satellite without actually going there. So this is what we try to do in planetary geology. Earth geology is different. We can do experiments, we can collect samples, and then we can come to some kind of a conclusions itself. So this is what we try to do in our planetary geology. Okay, so now this is what we said. So planetary geology is a very broad and it's interdisciplinary kind of a subject, because here geology, geochemistry, biology, remote sensing, all those we require data, or we require you have to work with all these type of groups itself. And there are also some more disciplines like cosmochemistry, petrology. What do you mean by petrology? So yeah, any of you have an idea? The petrology means what it does in petrology? Any of you have an idea what is the subject petrology? So this one, what does it do?
Study of rocks,
No,
sediments.
it is basically study of rocks, igneous rocks, metamorphic rocks, that's what we say. So this also comes, it is something like a neighboring discipline, like a petrology, study of rocks, then biology, and then of course geophysics also, because I will show you like Apollo data and other solid geophysics. So planetary geology, we have to work closely with all these groups itself. And so as already I mentioned you, so this planetary geology, it did not start with the moon exploration. It was already there in the long back itself, the planetary this one. But of course, the moon, once this Apollo, they made this subject extremely, the popular itself. And actual geological observations say, so like as already mentioned, you Galileo, so they have done with telescopes, they have understood in Italy, so many things are already there itself. And you can say the disciplines corresponding to planetary remote sensing. So generally, when people were doing remote sensing on moon, so they used to call the subject as selenography also. So these are some peculiar names. It is just essentially remote sensing of other planets. Say the selenography also they call. So planetary geology is not like it is like interdisciplinary subject, and you have to work closely with all these groups itself. And the subject was born long back, like in Galileo, once the telescope was invented, say. So the subject was born there, but only Apollo missions and moon missions, say, they made the subject very popular, and then they have brought like systematic procedures and other things came after this Apollo missions. So now these are the earliest drawings, basically, like one famous geologist, Gilbert. Okay, so in 1893, so they have observed this moon in telescopes, and then they have made these beautiful images actually. Okay, like for example, you see the craters, where the material has been there, and you can see some craters they have marked, and then approximately they have also, they have taken a section here. Okay, basically, and then this is a topographical data. So some sketches have been made by a famous geologist Gilbert. Okay, long back itself, in 1893, one of the earliest things itself. And this was one of the first digital image, you can say, which was for the Mars, which was done by a spacecraft in 1965. So you can see, so these are all the hand drawn, from the spacecraft. At that time cameras was not that this one, so they have hand drawn the, the surface of the Mars and others also. And this is a digital data basically, like you can see some numbers and then the colors, these are the very one of the oldest photographs which we have got, from the earlier flyby, or that orbiter or flyby missions itself. So now in geology, say, so geology is essentially, reasoning kind of thing. Okay, so I will show you also. So reasoning is the most important thing in geology. So you make a hypothesis, and then you have to provide some kind of reasons itself. So now, like you see, so emerge from bottom up kind of a thing. So early natural, the science geologists say they observed and interpreted the rocks and landscapes they encountered close up. So in our Earth, people, whenever they used to look at a mountain, so what type of rocks it consists of, how these mountains have evolved, and all those things people used to do in geology itself. So what they do is, the people generally, they use the synthetic reason. Okay, reasoning they give. That is, you compare, say, like for example, if you go to Kadapa Basin, or the Indo-Ganga Basin, or whatever, so they compare. Okay, the continuous activity of, they will compare this region with something else, other regions also, like analogies they try to give, and then they connect things, and then finally, they put together the thoughts and perceptions of how these things have evolved, and then what is the present state, how it was in the past, and then they will give all this type of interpretation. That is what essentially reasoning, geological reasoning, we say. So initially, so the geologists focus on formulation of some kind of a hypothesis, like for example, how Himalayas have formed, say. So they will have some kind of a hypothesis, like you say, Indian plate or Asian plate, or they would have collided. So there will be a hypothesis, and then they will cause a phenomena of interest, and then they look at the consequences of adapting this hypothesis, and then they try to do all these things. Like for example, say, why earthquakes occur in Earth? Now, what is the reason for earthquakes? Now, what is the theory? How what is the explanation for earthquakes in our in which occur on our Earth planet?
Due to the stress accumulation.
No, no, stress accumulation is fine, but geologically, why the stress accumulates?
The tectonic moments, sir.
Yeah, that plate tectonic theory, that Alfred Wegener's, right, plate tectonic theory. So how he started that theory, it is, he's also a geologist. What he told was, what was, right, plate tectonic theory. They said that all continents are previously there were one continent was there, and then slowly they broke up at each other, and then that was a hypothesis which Wegener gave for this plate tectonic. Now, how did they verify? So that was a hypothesis basically. Then how did they verify? They tested, right? Now, like India was also part of Africa. They tested some fossils, like in India and Africa, we had some similarities was there, like South America, Africa, that side, they tested the hypothesis, and then that theory was accepted basically. Okay, so this is what essentially a geological reasoning is. So you form a hypothesis, like for example, earthquakes are caused due to plate tectonic movements. Now, how do you have to test that hypothesis? So you take all the samples, the reasoning you have to give, and then finally you have to conclude, that hypothesis itself. So you have to test that hypothesis also. So this is what we essentially do in geological reasoning itself. Okay. So here we do these geological maps, to summarize, we prepare maps basically, like, this type of maps here. And then I will show you some more geological maps also. And then the geological maps generally, whenever you have seen the geological maps, they also give the age of material also. Like you see, what type of rocks they are and what is the age of this one, stratigraphy they say. So all these things, comes under this geology. Now, so now, but in the space age, say, if you want to do geological reasoning from the other extraterrestrial planetary bodies, say, so you have to go from top down basically. So top down means, as already I mentioned you, if you want to study moon, say, so how you are going to proceed? So we are going to send a flyby. So this orbiter, what it happens is it rotates, so you will have the surface images itself. Okay, so we go, so from the top, say, you will have an image. From the top, you have to understand what it is inside the moon itself. So that's what we call as a top-down approach, basically. Okay. So first thing, planetary surfaces, we see at them globally. Okay, like an orbiter or from a telescope, you see the surfaces, and of course at low resolution itself. And then we slowly go down. Okay, like we send rovers, and then we go down land, and then we may have to drill, and then maybe we will know the internal structure of the planet itself. So this is very the top-down approach. This is a word which we try to do in planetary geology itself. So now that's what we. So now once you do the global thing and then low resolution images, and then we will get finer details, as spacecraft sensors, on small regions at higher resolution, high images will come into picture. And then once the landers and rovers goes there, then you can do a lot of analysis, and then they do the experiments also. Or if you get the samples from there and if you can test it in the lab, say, then you will know more details itself. But only negative thing with these rovers and other thing is you can land a rover at one particular place, and geology of a planet is different. Geology of that particular place itself is different. This is one limitation. So, but overall in the planetary geology, say, so it is what they call as a top-down approach. So initially you start with the big, huge, the global images at low resolutions, and then you go down, and then you see you verify the truths and this one. So this type of approach is known as top-down approach in geology. So here there are some principles are there, like the problem of convergence. They say equifinality. These are some. No need to worry. These are just geologists. They use these type of things. So the top-down directionality, say. So it is enhances. This is convergence basically. So in this, the geologist must contend with the possibility that several effects may be generated by different combinations of causative process. So, like for example, you have to converge. Like I showed you these craters on Moon. So now how this? So now looking at this map, now you have to give the analogies, or you have to come to some kind of a hypothesis. So now how this region has formed, say like for example Tycho crater you are seeing, say, how this crater could have formed, how this type of things, how it will happen, what are the hypotheses, variety of hypotheses.
Meteor strike.
Meteorite strike, another thing,
So volcano, well, volcano.
volcanic craters are there. Like that, there may be a satellite impacts also. Somebody would have done a, you see, this type of a lander or artificial impacts also can happen. The satellite would have collapsed on moon itself, and then that also would have created something else also. And we don't know. This could have been done by so many hypotheses maybe there. Of course, now the hypothesis is volcano or maybe a crater, because we know the now the better we are in a better fashion itself. So now, so this type of hypothesis has to be done. So this is what we say principle of convergence. So some person will come up with this type of hypothesis. Some person will come up with this type of hypothesis, and they will in the low resolution. So because you can't go to that region, say, So it will be in a low resolution telescopic view. You come up this one. So the convergence we said. So all of them, all the experts, they should converge to a common hypothesis. This itself. So now this was a moon's thing. Initially, so did these features result from explosive volcanism or from meteorite impact? So this was a question. 30, 40, or almost 50 years back, say there was some group of people who said it was basically due to the volcanism and that was lava, something like that. Then the other group, what they told was, it may be due to the meteorite impacts also. So now how do you verify these hypotheses? So these are very, so if you want to verify, say, and these are all very low resolution, the telescopic views only. So you have seen from a telescope, and now you have to form a hypothesis and you can verify. So planetary geology, so initially we start with this type of hypothesis, and then, you send an orbiter, you send a lander, and then, the top-down approach kind of a thing, increased resolution, and then we do more in detail, and then we try to, confirm actually, okay, like they try to converge or something like that itself. So generally in the olden days, say, so these lunar craters, okay, whatever you see on moon, so people, were against this meteor impacts basically. So everybody was under the impression that this all has been caused due to volcanism only. But then slowly, as of course people went there and they have done the tests and other things. So this impact cratering, became very popular, and they've understood that, this is a fundamental thing which has created these planets and all other issues itself. So this is what we have to do in planetary geology. Okay, so you have to form a hypothesis and then you have to converge, and then they have done the most important thing in geology is analogies. Okay, of course, analogy is also very important in our civil engineering. So, like for example, in our civil engineering, say we have tested a beam in the lab. Okay, so once you do a beam in the lab, you will get the deflection profile of the beam, and then you will start finding deflection, that plasticity or plastic hinge forms and other things will form. Now, how do we give explanation for that? Now, what do we do? So you have tested a beam in the lab, okay, and you have tested until a steel beam, say it has gone up to the plastic hinge or whatever. So that is what it has happened until failure you have tested. Now to explain that phenomenon, so what do we do in civil engineering? See, how do we explain that process? What is that you try to do?
So we can plot graphs as tested graph.
What?
So we can plot graphs.
No, graphs is fine. You will plot the graph, experimental data, you plot it in terms of graphs, but how do you interpret it? See, as load increases, deflection also increases, that everybody knows. And if you test some other beams, you will get different graphs. So how do you explain this one?
So by
Yeah.
using formulas, theoretical formulas, we can
Yeah,
verify.
so what is that you have to do? Theoretical formulas, okay, or theory. So what you have to do? We write m is equal to a d square y by dx square or whatever. You solve that equation also. Say. So your theory also will give some kind of a deflection. So now you compare this with the experimental result, and then you provide some kind of analogy. Like you see, this beam deflection is less, other beam deflection is high. Say. So now you can say that you see maybe its Young's modulus is more, or EI is more, or the fluxural rigidity is more, fluxural rigidity is not fine here, or something like that. We try to give some kind of analogies. So now in our civil engineering or structural engineering, mostly in all our engineering disciplines, what we try to do, whenever you see any experiment or if you see any crack in the concrete, say, or crack or whatever you have, say, okay, stress strain curve or whatever you have. So we try to give some analogies also. Here also we use analogies, but we use from theory. Suppose if theoretical things are not possible, so we do some computer experiments like abacus, finite element simulations. If you want to test a highly like oscillatory kind of a surface a beam has, say, like irregular surface or something, you may not be able to give a correct theoretical expression. So you try to do it in finite element, and then you compare, and then you give some type of analogy, like why this beam collapsed quickly, why this beam has not collapsed, why deflection is more here, why deflection is not more here, like fluxural rigidity is high, or the shear rigidity is high, or the other things also. So like that we give analogies. Now in geology is also essentially about analogies only. But here what we try to do is, in geology, of course, now the computer simulations are also becoming popular, but most thing is here we also give a lot of analogies with when it comes to planetary geology, say we give a lot of analogies with earth itself. Okay, so that's the most important thing. So this what so geological reasoning says. So we use a form of analogy that takes advantage of observed natural regularities that suggest reasoning in which the newly discovered phenomena are compared to the phenomena already known and then understood. So like for example, if you want to explain Himalayas, okay, how Himalayas have formed. How do we explain how Himalayas are formed? Yeah. So what we try to do is, you take a similar kind of a thing, like some other place, or maybe instead of Himalaya, if you take this Andaman subduction zone, say, which all of like you see the Indian plate, Australian plate, or this one, say. So what we try to do is we try to give an analogy. So it is something like in Chile also we have a subduction plate is there, Pacific plate is going below. Maybe the same thing has happened here also. Like Himalaya, people say it's a continental collision. So like some kind of analogy. So you will compare Himalaya with something else and say some kind of analogy, and then we say why Himalayas have formed. We give this type of analogies, geological reasoning like that we give. Like as already I told you about the plate tectonics theory also. So what? So the newly discovered phenomena say. So if you want to explain anything new, so what we try to do is we compare with the already existing phenomena, okay, which we understand very thoroughly, and then making an analogy. Say we comment like how this would have formed or something like that. So this is what we say. So in this way, insights gained from comparison say. So they contribute to further investigations in a unknown phenomena itself. So this geological analogy say. So of course you will not be able to get definite explanation. So like why Himalayas means you can say this is a continent solution, but you don't know how much will be the height of Himalayas every year. If you want to come up to numbers or something, you will not be able to provide a perfect definitions, but some reasonings can be given itself. So this is what so analogies becomes very important in planetary, especially in planetary geology. So that's what we say, terrestrial analogs we say. Okay. So earth, of course, geological phenomenon earth are perfectly fine. If you want to know why Himalayas are rising or whatever, you can go and test GPS instruments or seismic data or whatever. You can test and then you can finally this one. But if you want to do geology of like I showed you what are the why mountains have formed on Mars, or why the craters have formed on Mars or Moon or whatever, then we can't go there to test and then do all. We don't have that type of a luxury itself. So in planetary geology what happens is a terrestrial analogs we say, like if you want to explain how a mountain has formed on Mars, say, you take analogy in earth. Actually you take a similar region, say, where you see that type of a phenomena, and then you create some kind of an analogy. So this is what we call as a terrestrial analogs, basically very important in whole planetary geology. So this subject is motivated by this terrestrial analogs itself. And now people are very much experienced. So like if you see experienced geologists, so like if you show the map on Moon, basically the craters or whatever things, so they do a lot of multiple hypotheses. Like I showed you for Moon volcanic crater at this one, and then whether it is a volcano or whether it is a meteor crater, say. So what we try to do is, you try to have an analogy, you compare this with the Earth itself. So like as already I explained you here, now, if you want to understand this Tychos, this region actually, so what is analogy you give? You have to compare this with whatever information we know on Earth. So you search in Earth, say, whether somebody has done similar type of a study, or whether there are regions, say, where you see this type of features. So using that, and in Earth you will understand very nicely. All the you can do computer simulations, you can do testing in the lab also. So using our Earth analogy, you comment on the formations on Moon or on Mars and other planets itself. So this is what we call as terrestrial analogs. So this is the most important thing in this itself. So this is what, so that is essentially what we do in planetary geology. So everything is analogies. So these analogies you can compare with whatever has happened in Earth, or sometimes if you are unable to do so, maybe you may have to create a computational model or some theoretical model, or maybe you have to draw some kind of analogies. So this is what, so this Gilbert, who is a very famous planetary geologist, who I showed you, right, that moon maps and other things. He has made the geological maps also. He said, so geology is essentially like investigators rather than the theory kind of a people. So theory kind of a people, what they do is they will derive some kind of a theory like Newton's laws or Einstein's theory or beam theory or whatever, and then we try to compare with the data and then we try to do. But in geology, what we try to do is we don't have any theory, we don't have nothing actually. Okay, so geologists what they do is though just like you would have only this image basically. Okay, now using this image, now you have to build a all the theory or all the details itself. It is something like investigation only. Okay, like if people in our crime, this one, so they will show maybe a photograph, and then you have to construct the whole process and the whole theory behind how it has formed and the importance, age, and other things itself. So this is what we. So that's why geology is essentially it is a investigation kind of a thing rather than theory itself. And of course, our things are much easy because controlled like in our civil engineering say. So if you want to understand why the beam behaves like this, steel beam, concrete beam, or something, we can do easily. You can build a computer model, or you can even build experimental model. You would have done in our experimental analysis courses and other things, and you can easily you can have everything is under control, man-made kind of thing. But the problem in geology is we can't do experiments. We can do some small scale, but it's a very difficult. We can't test a glacier or a volcano in the labs. How volcano can you build an experimental model where you can simulate a volcano? So it's extremely very difficult to build such type of models itself. Even the impacts also are very difficult. Are evolving mountain ranges, how mountains evolves in a laboratory room. Like you can't make a model of Himalaya in a laboratory, where and you can't even simulate an earthquake in lab. You follow. So these are very very difficult geological experiments. You can't do experimental things are not possible. So that's why planetary geology is very very challenging compared to theory. So in engineering, it is very easy for us. If you don't understand, you build a computer model, you do some theoretical formula, and then you can draw some kind of analogy, and you can explain the phenomenon also, like why this structure collapsed during an earthquake, why this structure is standing, why this structure is not standing. So you can draw shear force, bending moment diagrams, or whatever, and we can give an explanation. Or you construct a experiment of that frame, a scaled model, you test it in shake table or some this one, and you can give some kind of a physical this one. But for geology, the problem for geology is, you can't do experiments in the lab. Glaciers, volcanoes, this one you can't do in the lab. Extremely difficult, basically. So we don't have that luxury in geology. So what we have is only that, the graphs or the high resolution images. From that only, we have to give all kinds of hypothesis, informations, everything. So this is the main problem in geology. Okay. So now these are, so and I don't know how many of you know. So what is the qualification for an astronaut? So if you want to astronauts to say, what is the extra qualification they do? All the astronauts, so that when they are sending them to moon or any planets, all of them should know. Now, what is the qualification? They should, of course, they will be trained in how to land, in and other things also. But the most important, all the astronauts say they have to do. They should know what.
Some
Of
geology.
Earth and other respective
Geology. You are able
planets.
to see the slide, right? This one. I have put it in the
Yes,
full
sir.
flow.
Yes.
So the
Yes.
most important qualification is geology. You follow. So all astronauts, Apollo astronauts, or whoever had gone to moon, they have a degree, that MS degree, or you remember some small diploma or degree kind of a thing in planetary geology. So all the astronauts before when they are sending to moon, so they take them to all geological places. See, like for example, these were the Apollo astronauts where they went. They have been trained, so they have been taken to this Reese crater in Germany, because a lot of meteor craters are there in moon also, so that if they land, they should be able to tell actually the ground truth. So they have been trained in India, and in our India, I will show you the photographs also. We have a lunar crater. I will show you after some time. So where some many people from NASA and others, they come and they do a lot of experiments in lunar crater, which is in Maharashtra, in mitigate the impact. And then what is the best place in the world, for geology? For geology, which is the best country? If you want to see all kinds of geological features, volcanoes, mountains, plate tectonics, mantle plumes, all the rivers, that landforms, everything set. So which is the best country in the world which has all for geologists?
India.
Which one?
India.
No, which is the best country? I don't know whether you have seen that James Head video or not. That YouTube video, have you seen? So he mentions one specific country. He says it is a heaven for geologists. Which is a country? So that James Head lecture, he has clearly mentioned, which is the heaven for geologists. Which is the best place where you can see all kinds of geological features, most of the geological features, say. See, all of them are in Iceland. Have you heard Iceland? See, can you see Iceland map in the Google Earth? See, what is the speciality about Iceland?
Located near to the poles.
No, that is near to the poles. But what is the geological advantage with Iceland? So if you see Google Maps, okay, so I will show you. So if you see the plate tectonic maps and then the Iceland say, maybe I will show it at a later stage, maybe. Okay, fine. I will show it later stage. I don't have that image now. You can just see in Google. See what happens is Iceland is basically located between the junction of two tectonic plates, Atlantic plate and then Pacific plate. So that is basically a mantle plume, this Iceland, and it has a volcanic. Everything is there in Iceland. Okay, so generally all the astronauts say they are taken to all these places, and then they will be very well trained actually. By looking at the rock itself, they should be able to tell us what type of rock it is, whether it is a meteor crater or whether it's a volcanic crater. So they will be doing a lot of training basically. Okay, and you can see this person, this E. So he is a shoemaker. He is one of the pioneer, we can say, planetary geology. So these people, and that James Head lecture you have seen, that James Head also. So these people, they give training to the astronauts actually in for planetary geology. So once they land there, they should be able to tell, whether it's a meteor crater, what type of rocks are there. Of course, they will bring samples also. So because the human eye is most powerful, so they train them. So they take to all these excursions, and they train them in this thing so that they can find out analogy also. So once these people have seen a meteor crater, volcano crater, and other things to say, so it becomes easy for them once they land Moon or Mars, they will be able to identify the analogy, and then they can give some kind of a conclusions and the ground truth. So this is the most important aspect in for astronaut training also, the planetary geology. Okay, so this is also like, so this was examples for Mars also. They have given a lot of analogies, like these are the that Hawaii volcano. So because in Mars also I showed you, right, that largest mountain, that I think tallest mountain, in Mars planet also, which has been formed by that Olympus moons or something for volcanoes. So you can draw analogy with this Hawaii volcano here, and these are they call this as, I think, yardans. Okay, wind erosion, wind-based erosions also, because you see in Mars also. Then these are something like the sublimes and Beacon Valley or dry valleys in Antarctica. Then they do experiments also, like groundwater seepages and others. They have drawn analogies, and then they compare this with the Mars photographs also. So I will just to show you some interesting the papers also. So you can see some interesting. You people are able to see this one.
Yes, sir.
Can you see this paper?
Yes, sir.
So now this paper is essentially about yardans. Yardans are nothing but wind eroded ridges. Okay, so it is a mountain which has been erosion happened due to wind itself. Because on Mars also has an atmosphere, dust storms and other things also. So these people, what they have done, it is also analogy paper only. So what they have done, they are comparing Mars with. Can you read here? Which basin they are comparing? Yeah, so they are saying that Mars, whatever you want to do, and if you want to understand this wind type of erosion of mountains in Mars, they are giving analogy. So this they are comparing with Kaidam Basin in Tibet basically. So if you see this paper, it's very nicely written up paper. So you can see Kaidam Basin. This is a Tibetan plateau. So this is a Kaidam Basin. So they have collected all the geology of this Kaidam Basin itself, and then this is a geological map, they say. So Pliocene, Miocene, these are all the ages basically. Okay, so they do all these type of Holocene, when this has formed and other things also, and then the climate, all those things they will find out, and they are drawing this analogy to a place in Mars actually. So that is the reason is Medusa Fossae formation. So this is a place in Mars. So this region. So this is a total topography of Mars. So this region say, so this region also you will see this type of wind erosion, this yardans in Mars also. So now they are trying to build an analogy, comparing with the Tibetan thing with the Mars thing itself. So this paper, they have done nicely, for that Kaidan basin say. So these are they have done. Can you see here? No. So these are all wind erosion. So because here the wind speeds are very high, so these mountains got eroded actually. So the wind has cut these mountains also. You can see these are the sediments, debris, gullies, sand ripples, everything they have done in this Tibetan basin. All the geological excavations they have done in the Tibetan basin, and finally say so they have done so many calculations like what is the height. Oh, sorry. Now, what is the height of that mountains? How much it has been eroded? So all those details have been done. So these things they have calculated, like you see the crust, how much has been done, what is the windward phase, wind, which direction wind is flowing. In that direction, you will have a lot of erosion. So they have got all these, this type of ridges they have observed in the Kaidam Basin. So many photographs they have taken, and then they have given a nice understanding here. But the target is no. So using this data sets, so Tibet, one can go, you can see the people, they have found out the salt crust lines. You can see all these details they have calculated from the Kaidam basin, and they have drawn some graphs itself, morphometry, this metry, and other things. They have done all these calculations, relative frequency, how this process of yardans have happened in Kaidam. So they have discussed like embryonic stage or whatever. They have done all these details. How it has grown. Now, initially it was like this, but finally now where they are there and how these things are getting eroded, and now where are in the receding stage. So they do for the Kaidam basin. Now, once that is done, say, so now this is the Helios Dorsa. This is a region in Mars basically. So this image they have taken. Okay, so this image is in Mars. This image is in Kaidam Basin. Okay, and this image is in Mars, and this is in Kaidam Basin. This is in Mars. Now you put an analogy. Now the same geological features you can observe on Mars also, and you make analogies. Say. So then you can draw some kind of conclusions. Like in Mars also, you will see these type of things. So this is the reason why, like you see, Kaidan Basin say, you see these type of features. Okay. Now in Mars also, you are having these type of features. So now they can have a conclusion which direction the wind has blown, how this erosion has happened. So all these things you can easily study, by type of analogy. So this is one typical. I will send you this paper in WhatsApp also, so you can study. So there is a nothing. So you do for our, in the Earth, and then you put analogy for other planets. This is what we call as a terrestrial analogy. So this is the only way we can understand, the geological processes on other planets. So here, this paper is essentially about wind erosion of these mountains and others also. So they call this, the geological word is Yardan, they say, but it is essentially wind erosion. The mountains got eroded due to wind, huge, the wind speeds and others also. So this is one typical paper. Then this is also one more paper. It is an ICARS journal. Okay, so this also you can see thermal contraction crack polygons. Okay, so this is also on Mars. It seems they have seen this thermal crack. So now what they have done is here also you have to draw an analogy. That is a terrestrial analog studies itself. You know this person, right? James Head.
Yes, sir.
Yeah, because you have watched this video only, you followed. So that same, and he is a journal, ICARS, which is very famous. I told you, right? All the important things comes in these journals also. So he has done the analogy. Okay, so this is what they does. So they will see these type of. I also don't know. So these type of things they observe on Mars, the thermal contraction cracks and other things also. So this they have observed on Mars, that high-rise images or whatever that QGIS software say. If you open up the topography maps, you can see all these things itself. And now, why this is happening? What is the reason behind this? Or what are the details of this one? Now you have to explain. So he has got all these details itself. So now what he has to do? Now he has to draw a analogy. So he has done some polygon Antarctic dry valleys he has taken. So in Antarctica, say. So they have taken this type of dry valleys. They have taken photographs, and the geology of this region is very well known. So now you compare this with the Mars and then try to explain what is the reason for Mars itself. Okay, so these are the how people try to do this type of unlock. So this he has explained about this hex intersection, that that complicated things which I have also not studied, but this is what they do. Terrestrial analogs will say, like how this has formed the same. So this is a beacon valley. Okay, so this is an Earth. So you compare this with on Mars also. You can see this type of polygonal structures. You can see here, right? You will see these things in a dried lake beds and others also. So similar things are there on Mars. So you explain by giving some kind of an analogy. Okay. So there are no equations, in our civil engineering say. Lot of equations, theoretical aspects we do. But in planetary geology, say, the theory will be less, but write-ups will be very more. You have to write it in detail, and you have to justify your hypothesis. The terrestrial analogy, you have to show a lot of support actually. What is the equivalent thing here? So it is mostly about the writing portion in this planetary geology. And then finally, you should be able to explain why this has happened on Mars, what could be the reason, and other things also. So this is the most important aspect in this one also. Now I will show you one more interesting thing for this. One more analogy I will show you. This is for the you can read this one. This is a lunar crater. Okay. So as I told, right, Senthil Kumar, who was supposed to teach this course, but anyway, something NGRI scientist himself. So he has done. So now what he has done is he has gone to this lunar crater. Okay. I don't know how many of you know this place. All of you have known this lunar crater. Have you heard this name? See, lunar crater, where it is located? All of you know this one? See, any of you heard this lunar crater? Where it is located? Kshitij or Utkarsh. Have you heard this place?
No, sir.
First time? Okay.
It's a lake, sir.
No, it's a lake only, but where it is located?
Somewhere in Maharashtra or somewhere.
So you can see in Google Earth itself. I will just show you. You can see this Google this one. So if you put up, you can see the analogy, lunar crater, say, okay, which is in Maharashtra. You can see here.
Yes, sir.
It is visible, right? It is a lunar lake, they say. Now you see what is analogy for this, how this lake has been formed. You can see here. So this lake was also, a lot of debates was there. Okay, so some people said, 30 years back, so this lake was done by volcano, because Deccan basalts are there, right, in Maharashtra. So they say that this is the place where the volcano moved, and from here only basalt came, like that. That was a theory. But then slowly, a lot of geological evidences, impact cratering, the understanding was much improved. And then now the thing is, it has been hypersonic velocity. I think the velocity of impact was something around 16 or 17 kilometer per second. Very high impact happened something around 50,000 years or maybe 1 million years ago, and this lake was created here. And as already I told you, this lake is extremely famous, and this lake is used to train. This lake is who comes to this place actually. If you want to go to, all the astronauts say, if they want to go to Mars or other places also, they bring some of them, they come for many NASA, and many people say geology, planetary geologists has come to this place, and they have done a lot of study in this lunar crater. Okay, very famous place. And if some of you are nearby, you can go whenever you want it. And one more crater is there in our India, which is not explored, but now people are there. The Dhala crater. How many of you heard about this Dhala? First time. So this is also one more crater. You are seeing, right, this place. So it is, I think, if you zoom up, where it is located, you can see it is somewhere, I think, Madhya Pradesh or it is located in Madhya Pradesh near Jhansi. Okay. So if you zoom up this region, say, so this also a crater. If you see the images, from this one, see how does it appears? No. All of you can see, right, this shape. No. Yeah. What is your comment after looking at this?
Looks very small.
Of course, the dimensions it is in Google Earth. I'm showing you. You can clearly see, right? It is also maybe done by impact, or we don't know. Of course, this crater has not been studied in detail. Now only people are exploring this one, so the subject has evolved. But these are some of the places where one can explore this impact cratering. Okay. So anyway, so just so that you should know these very important things. So now I will just let us go back to our slides. You are able to see, right, this line? Okay, so this is what we do, terrestrial analogs we say. So they are very, very, the important things in our planetary exploration. So here also, when you propose a hypothesis, say, so there is something like, methodology is there, like you say, consistency you should have. So whenever you have a contradiction or, geological phenomena, you should not have any contradictions actually. Like, if you say that if you have two theories, say, both of them are agreeing, they should not be contradiction, both of them should converge. Okay, the consistency we say, then coherence also. So when you are explaining any phenomenon, say, so if you study those papers, you will understand in detail. So then explanation, you have to give a nice explanation also, so that there will be a coherence and it should match with all other observations also. So these are some of the things, and then consilience also. So these are also three words. Consistency you have to be there, coherence has to be there, which matches with other things also, and then consilience. Like if you have a jumping suddenly, as already I told in planetary geology. So first things, you will be having telescopic images. So from the telescopic images, you infer some hypothesis, and then you do something. Say tomorrow, you may be getting high resolution images. Okay, so then there's a consilience comes with the picture. Like jumping together, of a knowledge, explanatory surprises can happen also. So this is also very important. Okay, consilience, coherence, and then consistency. Because our technology is improving, whatever we understand about this planetary, this geological process, they are going to improve basically in future. So all these three things becomes very important. So that's what they say. The newly recognized phenomena, are clearly related to the phenomena under investigation, and that they are adequately explained by the tentative hypothesis that was originally proposed in a more limited context. So initially from telescope images, you make a hypothesis. Say tomorrow some extra knowledge comes, once again, if you do consilience, that becomes a problem. So anyway, the consilience does not truth via formal logic, but its operation has been recognized to be, of course, this is what they say, most fruitful of scientific investigations also. So these are the process. If you want to do this terrestrial analogs, you have to follow these rules also. So this is what, so the basic approach is in our planetary geology, we have three elements. One is, analysis of the spacecraft data, that is a high resolution images or maybe samples or whatever we have. Then of course, nowadays, because the computers have become very powerful, say, you may not be able to simulate an earthquake in lab. You may not be able to simulate a volcano or glaciers or impacts or something in the laboratory, but you can simulate them in a computer actually. Now our supercomputers have come, so now the laboratory computer simulations have become very powerful, and we can simulate a planetary environment also in our computers, like finite elements and other things also. So this is also a very important aspect. It was not there previously, but now this has also become a very important aspect in planetary geology. And then the planetary geology, the fundamental thing on which planetary geology stands is terrestrial analogs. So these are the fundamental, we should have some kind of analogy, and then only you will be able to explain. So if you combine computer simulations with terrestrial analogy and then with the data set, the things becomes much more, your hypothesis, you can test rigorously, and this you may able to extract, the truth itself. So of course, so that's what we said. So there are some papers where they do only A, B, C separate also. But if you make it collectively, say, you will be able to, understand the past and present, the surface time histories also. So of course, the starting point is the data only. Without images or without any data, you will not be able to do anything. So this is a starting point. So now once these maps comes, the terrains, varieties, we identify all of them, and then we try to do hypothesis, and then we try to get some kind of explanations, like as already I told, computer simulations or terrestrial analogs and other things we try to do. And of course, when you are going this one, so now in future, they may send more missions and you may get more amount of data also. Then of course, new ideas may emerge, or maybe your hypothesis also may prove to be correct also. Okay, so this also you have to keep it in mind in planetary geology. So like for example, so this is a computer model, So right now, of course, Meenakshi, she is doing this moon simulation. So we have built a huge computational model where you can simulate these quakes on moon itself with whatever information we have, say. So we have built a computational model. And now this is Apollo data. See, Apollo missions, they have put a seismograph and they have recorded the data on moon, and this data is available open. Anybody can download this data. So what we try to do is we build a computational model, and then we simulate these time histories also. We try to explain basically. Okay, so what is the reason for this, and it is like a computer analogy. So we are drawing to explain moonquakes, analogy with our computer simulations also. So that's the first. So as already I told you, the planetary geology. Of course, it was done long back itself, but it became more popular after this moon itself. That is, the craters on moon is the first step where this subject has become extremely popular. So for moon set, so the starting was with telescopic views. Okay, so from the telescopes, the people used to do, and then they got some kind of theories and other things also. So now once as already I mentioned in those days, the support the people was understanding was the craters or whatever you see on moon, they are all of volcanic origin. They were all due to volcanoes. That was understanding. Okay. Now once we send the data like spacecrafts went and all those things like impact versus volcanic origins, and then the images also people got it, and then both the ideas, both the hypothesis was accepted also. Then volcanic crater, and at that time also what happened was the volcanic craters are very well understood on Earth because now you remember it, the Tonga recently also many volcanoes are erupting in Hawaii and others. So what happened was our understanding of volcanic things are much better, okay, compared to impact craters. And the unfortunate thing in Earth is, if you have an impact crater also, say what happens in Earth? What is the problem if you have an impact crater? Say what's the main problem in Earth?
Due to the tectonic activity, it will get lost.
So because of tectonic activity, and then the Earth has atmosphere also, weathering happens. Now you see the lunar crater, say. Now lunar crater, when it was formed 50,000 years or 1 million years ago, it will look different. Now if you go to the lunar crater, you have a lake, weathering has happened, soil has come, you see, the whole things got destroyed actually followed. So, the impact cratering was not much, this one was there, but everybody said volcanic was very well understood actually. Okay. So that's what we said. So the impact cratering was not, people said on moon, all craters are volcanic origin only, but impact cratering was not taken in the olden days. But then as more and more and more and data came into picture, now the support for this impact cratering became more dominant, and now we have understood these things in a better fashion. That's what I told. This is consilience. Okay, that important thing I told you. So these are consilience. This word, as more data becomes understood, say, then the together jumping, the new things also may come up basically. Okay, but of course now in olden days, so for this impact cratering also, like people started in 1880s, a lot of experiments was done in olden days itself, because impacts simulating is very problematic. So this Gilbert I showed you, right? This is a famous geologist who has drawn the images of moon craters and others also. He did some type of experiments like a mud he used to take, and then he used to take a cannonball, so he used to drop basically. Okay, and then you can see how this crater has formed, how much is the depth of this one, what type of features you can see, and then he used to compare this with the moon's craters itself. And then he used to tell this is maybe due to a crater analogies he used to draw with this simple experiments. Then in NASA said they built this gun basically. Okay, they like to simulate impacts projectiles which can travel as high as 7.5 kilometer per second. And because if you want to understand impact cratering on moon, say, because there is a vacuum here, there is no atmosphere, you should be able to simulate that planetary things also in your experiment. So they had a vacuum chamber, and I think this is a gun which was done, and then a lot of experiments have been done here to understand the cratering patterns and other things also. And then I think they improved this experimental facility to simulate reduced gravity. Say like impact on moon is different, impact on earth is different, because earth has atmosphere, moon doesn't have atmosphere. Then moon's gravity is different, earth's gravity is different, so the velocities may be different. So they have simulated these type of things, they built an experimental facility, and then they have done a lot of tests actually. So through this test, people understood this impact cratering, how the craters are formed, and then they compared with this moon craters and this one, and this subject evolved, and then the support for this hypothesis support has increased basically. Okay, compared to the volcanic origin itself. And at the same time, when these experiments was carried, say this I showed you, right? The Gene Shoemaker, who is a USGS geologist, who trains the astronauts, say, on these geological aspects. So he was one of the pioneers in this planetary geology. So because at that time this crater was there, because as already I told you, the most important thing in planetary geology is analogs, terrestrial analogs. So this was a person who did a lot of study in Arizona, that Meteor crater. So this is a crater in Arizona. Okay. Now also you can go and see also. So this crater is 1.2 kilometer in diameter. Okay, and the 30-meter iron meteorite some 50,000 years ago, they say. So this crater is very well preserved. So this shoemaker, he did lot of study on this meteorite craters, and then he established the terrestrial analogs using this craters also. And then there was also experiments like the NASA's gun or whatever these experiments was there. So they had results from experiments. They have a terrestrial analog was there, and computer simulations also slowly came up, and then this theory got this one. And then he also found out that meteor crater, he has done a lot of field studies, and they have discovered these two the rocks, cosite and stishovite, the high pressure forms of quartz actually, because during an impact, say, there will be high pressure shock waves and other things. So these quartz, these are the very high pressure forms. So he found out actually, and then gave a support that this Arizona crater was formed due to meteorite impact or something like that. And finally, remote sensing came up, and then slowly the subject. And the 1960s say. So what happened was, people started doing nuclear explosions. Okay, at Nevada test site, even USSR also has does lot of nuclear exploration. India also has done Pokhran test and others also. So due to these explosions, the craters also used to form. They used to do nuclear testing below the earth. So due to that also you will see a crater, and then people started looking analogs actually between this crater and the moon's crater, and then trying to explain whether that has been done due to impact cratering also. Like this, slowly, the subject has evolved, and then computers became popular, and then nowadays nobody does nuclear explosion because you can simulate it on a computer itself. So a lot of computer codes was developed, and so the combination say. So this subject also evolved, and then so this started the planetary geology also. So this is what I showed, the material crater. This is one of the fundamental crater. You can say which started our planetary geology also. Okay, and this is our lunar crater. So lunar crater also, as already mentioned you. In the olden days, they thought it was a volcanic origin, but then our NGRI people, then even USGS, some Japanese people also, they came and they have done a lot of studies itself in the lunar crater, and they say that this crater also was formed due to this type of impact. So in the olden days, say, there was a meteorite, just impacted here, and because the velocity is some 17 kilometer or 16 kilometer per second, hypersonic kind of thing. So what happens is, because of the heat, it got evaporated and this crater formed. So when there is a crater, say, the material whatever is here, so that's what they call as ejecta. It just fell down, and it just you can see this ejecta up to far away places itself. And then this was very well understood. This one, so I can show you this paper also. So it is visible now. So this is that lunar crater paper. Can you see, right? So this was also based on the impact itself. So now you can see this is like, so the impact happened in this region. Okay, 1.8 kilometers the diameter here. So what happened was, when the impact occurred, say, the material it got ejected and it has fallen all around the lake actually. So this green color you are seeing, right? So this is what they call as ejecta. Okay. So these people, this Senthil Kumar, these people, they are geologists. They have gone there and they have found out all the ejectas actually, how much distance the material fallen off, and others also. So they have got all these details, and they have done a lot of studies in this region actually, like rim, delta, and this one. And they have done, you can see, and they have found out these are the ejecta boulders. You can see, right? And if you, when you go to the lunar crater, say, so this boulder was initially located here inside the lake actually, due to the impact, say. So these boulders, they just flied off in the air itself. So this is what they call as ejecta boulder. And when you go to that place, you can see now weathering has happened in that region, but you can see small boulders, and all those high pressure quartz and other things also. Everything you can see in this region also. So the geology, you can see they have done, like Brescia, they have done the geological things also. They got all these details, and they have done a lot of studies. What is the physical property, and finally what they do with this paper, what they have discussed is so all the details they have done, and they have given the analogy. Okay, like this analogy they have given for this crater. So this is a crater, okay, which is in Mars, Arcadia Planitia region of Mars. You will see this type of the crater, and this image also they have used, and they have marked all the ejectas and others also. So now they have drawn an analogy. So if you study lunar craters, say, And whatever lunar crater it is applicable, say same thing you can equivalent is this the crater. So this they have done analogy, and then they have explained like what has happened, analogies and other things they try to do here also. So this lunar crater is a very important aspect here. So very important. So like okay, so this is how people try to do in the planetary geology. Okay. And now this is also one more very important crater in Canada. Okay, so here also astronauts are taken for the that is a training. Okay, how to identify whether it's a crater or not. These geologists they explain them. How do we identify what is the speciality of this crater? How the crater looks like? Suppose if they land on moon or even the robots, the landers if they go where it has to go. How do we identify all those things? Of course, this has got eroded by glacial lakes and other things also. So these are how we try to do this terrestrial analogs and other things also. So that's what we said. So terrestrial analog is very important in the planetary geology, and of course this subject has evolved like anything. Now we are having high resolution cameras, like in your mobile camera. So 108, I think pixel, huge things are there. So all this mobile camera, all those technology came from space only. Forward. So in the 1970s, pixel size was 60 meter or something like that. But now you can 6 meter 30 centimeter resolution you can see the planet thing, okay, from the orbiter itself, not from the lander. So when the orbiter say you have the topography images, you have the images also at this extremely high resolution. So 30 centimeter means you can identify small boulders, boulder tracks you can observe, landslides you can see, everything you can see through these high resolution images itself. So now studying these high resolution images, now lot of gully systems, water flows, volcanoes, all kinds of things became very very easy. The analysis became. Of course, all the terrestrial analogs you can apply only to the terrestrial planets. Like whatever you see on Earth, say it is equally applicable for Mercury or Venus or Mars or Moon actually. But now, can you do this type of analogs for Jupiter? No.
No, sir.
See, you can't do because there is no analogy for Jupiter. Jupiter is not a terrestrial planet; it's a gas giant. We have no analogs. That is not understood. Even not only Jupiter and Saturn. Suppose if you see this, these I told you that Pluto or some other planets, icy planets are there. Analogy becomes very difficult actually. So whatever success, 100% success is there on terrestrial planets. So if you want to explain icy giants and other things also, maybe Antarctica, you follow, right? People are now trying to do analogy to do for the that Enceladus moon or Europa and other things also, icy satellites. So these landed missions are going to plan, and maybe in future, this may going to come up actually. Okay, so fine. So I will stop here. If you have any doubts, you can ask me. We will continue in our next class.